Well, hello, everyone. Ryan with Sign Calibration School and the Metrology Today podcast. And welcome to season 3 of the podcast. We've been on a little bit of a hiatus due to just being busy at the school. Haven't really had anything since last MSE. And you guys keep listening to the podcast. People keep requesting to come on. And so guess what? We're going to have another season. But this season's going to be a little bit different. As you can see, or if you're on our YouTube, you can see me. Our podcast, we're going to release the video for podcast as long as we have it. And so if you're listening to this right now on Spotify or Apple, iTunes or the podcasting platform for Apple, whatever it is, you can actually see this podcast on YouTube, our YouTube channel, Metrology Learning Network. So a lot of exciting things planned. You're going to hear a lot of announcements coming up soon about training opportunities. And in general, as you can see behind me, this is our Sign Lab. So this is our online training platform where there's going to be some free training out there for all of you. And to be clear, if you're listening, you've been doing this for a long time, these are projects that are related to people that have never heard of metrology before in their lives. But plenty of you need training or there are topics that maybe you don't know a lot about. And so our YouTube channel is going to be a location for that. So please follow our YouTube channel. If you know people that you want them to get interested in metrology, or you have brand new people to metrology and calibration, have them subscribe to the YouTube channel. We're going to have a lot of interesting things coming up, both on the fun side of metrology as well as learning. So those things will be coming up. Now, as for our first guest, we have Paul Reese, who is friends with Henry for a long time. And by the way, Henry is going to be somewhat of a co-host for most of this season. There will still be some episodes that I handle on my own, or maybe we'll have a special guest host. But Henry is going to be my primary guest host during this season. Now, him and Paul have been chatting for years. They have good times at conferences and get lost in chat with Dillip and others for hours. And so I was really happy to get Paul on the podcast. I think you guys will really enjoy the way that he talks about metrology and the way he teaches things. Paul is very good at explaining some of the concepts that maybe are unclear to some of us. So a little background on Paul. Paul graduated from the University of Central Florida in 1993 with a bachelor's degree in electrical engineering. He spent 18 years as a metrologist working in the primary standards lab at NASA's Kennedy Space Center. In 2012, he left the aerospace world and joined the pharmaceutical industry, where he currently manages the Standards and Calibration Laboratory at Abbvie in North Chicago. He published numerous papers on measurement, decision risk, and contributed to the development of the ANSI Z540.3 Handbook and the ISO 17025 Handbook. This was a true pleasure. Please enjoy the rest of the season. We have a lot of surprises for you. And without further ado, on to the episode with Paul Reese. Thanks for watching. Well, welcome everyone. Obviously, if you're watching us on YouTube, this is our first video podcast that we're releasing. We did record video for, I think, most of the previous podcasts, but we just hadn't released any. And so today I'm very happy to have Paul on. Welcome, Paul. And
Yeah,
of course,
thank you so much, Ryan. Yeah.
And of course, Henry, who's going to be co-hosting many of these throughout the season. Welcome, Henry.
Welcome.
But I figure, as always, like we usually do when we have a guest, the most sense is to start off with Paul's background. Paul, do you mind telling us about your awesome career in metrology, and how did you get into this crazy field?
Yeah. Well, thanks for having me, Ryan. I appreciate
course.
you and Henry both. Yeah, it's just it really is an honor to chat with you guys. I always at the conferences and stuff enjoy chatting with everybody, but it's a real pleasure to do this. Yeah, so like everybody, we just end up in metrology. We don't ever plan that as kids growing up saying, "Boy, I want to be a metrologist when I grow up." And not only that, but most people don't even know what metrology is. Yeah, so if anybody's watching this, they obviously do know it's measurement science. But yeah, so my foray, I guess, into the world of metrology was I went to the University of Central Florida. So, I have a bachelor's in electrical engineering. So electrical is my background, and I've been kind of interested in, electronics my whole life. So that degree was an easy kind of picking. But so after I graduated, my first job, I went to work for a place called Graysby Optronics. And Graysby Optronics was a company that used to be United Detector Technology, but Graysby Optronics was an optics company where we manufactured light measuring equipment. And so I really got into photometry and radiometry, and I still find that one of the really interesting subjects in metrology. It's fraught with problems, which is why I like it so much.
Yes.
But yeah, so that company, we had an on-site calibration lab where we really just recalibrated all of the instrumentation that we sold to customers. So we had a radiometry, photometry, metrology lab there. We sent all our standards directly to NIST and had some really sharp engineers working for that company in optics. In fact, they even made a couple of standards that were used by NIST. They were QED, or quantum electro dynamic detectors, I think, and they would do like almost like single photon counting. They were trap detectors
Wow.
for doing light measurements where you really got like as close to 100% absorption as possible. So yeah, so that led me into what is metrology. I did not know what metrology was, and this was in when the middle of '94, I think, is when I went to work there. But yeah, light measurement is super interesting, and so I learned about what metrology was. I spent a lot of time on the phone with customers. I was actually an application engineer when I went to work there, but I got
Oh,
to know
okay.
the metrologist there. His name was Ricardo. I can't remember his last name, but good guy. And so yeah, I learned what metrology was, and on the phone, I would have to ask customers that would say, we want to send this item in and have it recalibrated. I would have to say all these numbers and words that I didn't know what meant. I would have to say, would you like a NIST traceable calibration, or do you need a mill standard 45662A calibration, And I really had no idea what any of that stuff was, but I learned over time, and so I only really worked there about 3 or 4 months, unfortunately, because after I graduated college, I'd sent out like dozens of resumes. Back then in the mid '90s, it was kind of tough finding jobs and stuff, especially for a new graduate. So had been working at Graysby about 3 or 4 months, and one of the contractors at Kennedy Space Center called, which was right down the road. I lived in Central Florida for most of my life, and yeah, so they said, yeah, we got your resume here. We would like to interview you. And I'm like, oh my gosh, and I felt this incredible sense of dedication and to Grays, because I figured I like the people I work with there. They had given me a shot. My green, wet behind the ears, new engineer out of college, and they had given me a shot with basically no experience. So I was really kind of torn between, but I figured, hey, it can't hurt just to interview, because if I interview and they don't call me, the decision's easy. There is no decision to make.
Right. Yeah.
So yeah, so I went out and I interviewed, and it was the first time I'd really been in a lab that was, just mind blowing, really high end primary standards lab kind of stuff. And they did, of course, everything. They supported, math and dimensional and electrical and all of this stuff, and photometry and radiometry as well. So I think the fact that I could spell those words and had heard of metrology, and on my resume even before the Graysby, when I'm still like a senior in college, one of the things I'd put on my resume that I think probably caught their eye, as I said, something to the words of, whether this was true or not, but, excellent working knowledge of all types of test and measurement equipment, because I'd grown up, with electronics and soldering and doing, had an oscilloscope when I was 10, and stuff like that. So,
Nice.
so I think they kind of honed in, oh, he knows what test and measurement equipment is. He might not know what
It's a good
metrology or
start.
calibration is. Yeah.
But did
I know.
you? I mean, we know now that you know.
Yeah, but I was, although I didn't know really anything about calibration, I did like tinkering with electronics and had a, pretty good background there. So it was just when I went out to Kennedy and interviewed and saw these different labs. But I remember like the first thing that I thought, and Ryan asked, how did you get into metrology? So the first thing I thought when I went out there, and they're explaining to me about these, resistors and voltages, and we make these really precision measurements on them and stuff. And they start talking about, rudimentary, kind of talking about uncertainty and stuff. And they're like, I remember Perry King was the guy that kind of interviewed me and that I worked with and really taught me electrical metrology. And he was saying, yeah, we monitor these, and when they're uncertainty of like, a tenth of a part per million and stuff. And parts per million was something that like I thought chemists talked about and stuff. I was unfamiliar even with that term. So I was like, when I went home, I got to thinking, it's really cool, but is my job really going to be to determine whether that 10-volt voltage, whether the, seventh decimal place is a 8 or a 9? Does anybody really care about that, And but
Right.
of course, in hindsight, we absolutely do care about those things. So it takes a bit to warm up. I think we all probably know that about metrology, that it's not the glamorous, the sexiest, the most incredibly compelling thing that just captures the mind and hearts of kids. And that was the other thing about Kennedy. It was the Space Center, and I'd grown up in Central Florida, and the idea of working out there, at NASA and stuff was just it was really too good of an opportunity to to pass by. But I do remember for a long time in my life, when I told that story, I would say it was the hardest decision I ever made, to walk in there and tell a boss that had just hired you 3 or 4 months ago that you were going to leave. And I felt an incredible amount of guilt about that for a long time, but he was very good about it and totally understood. And, so it all worked out there. But yeah,
It's the Space Center. You
yeah,
got to take it.
how are you going to say no,
Well, I think a lot of that initial story, hiring managers and new technicians will sympathize to your story, because I think a lot of hiring managers still in that situation where, they're just trying to find anybody with some sort of knowledge, right? There's some sort of experience to bring them on board. So
Yep,
very
that's absolutely
relatable.
true.
And then I
Yeah.
think we all feel very overwhelmed when you start in this field until you start to get a little warmed up.
Yeah, there's a language barrier too, especially if you work with people that have been in it for a long time, because we all take shortcuts in our language, and I've always been sensitive to that. It's like, even listening to surfers talk, it's like, what are they talking about? You don't know, because you're not in the group. And our guys out at Kennedy would just talk about, yeah, it's about 2 parts low. They wouldn't even say parts per million or ppm. They would just say it's 2 parts low. What does that mean? And they would refer to like model numbers of dozens and dozens of pieces of equipment, just like it was second nature. In fact, I tell this story too. It's like like the Hewlett Packard 3458A digital multimeter is just one of the, the workhorses in a good metrology lab. So the 3458, they wouldn't even say all the languages. They would just, other technicians, they would be like, hey, can I borrow your 58? And they would just, so there's all of that kind of old school language that it takes when you get involved in something totally new to you, that it takes a while to warm up to and really know what they're even talking about.
For sure. What was it like working there?
It was great, and really, very, very fortunate. I always say I just dumbed into that job, because again, I wasn't looking for a metrology job. I was a young grad just looking for work. But it was really amazing. I had a lot of people. Some of the older gentlemen that I worked with out there were there in the Apollo days, and so a lot of history there. And those labs had been the building that I worked in was the CIF building, or Central Instrumentation Facility. And it had been built in the late 50s or early 60s. It was one of the oldest and one of the first buildings built when NASA was it was started up. I think the NACA was the predecessor to NASA. It was like the National Committee on Aeronautics or something like that. But they built that building as an instrumentation facility. So the lab that I worked in was an RF shielded room. And it was, you wouldn't know it to look at it. It wasn't like a copper room. It was a drywalled or plaster room, I guess, at that point. But it was, it had shielding all built into all the walls, and the mass lab was an isolated slab, and just all this stuff. So it was nice
Wow.
it was an older building. And I've never been, try not to be, like a pretentious guy at all. I didn't have nice office furniture when I went to work there. You get a metal chair to sit in, it was built in 1950s. You're at a metal desk designed by the government to, survive World War III or something, So it was an older building with older furniture and stuff. And, but it was, but the equipment there was just state of the art. They had bought some of the first resistance bridges from Measurements International, Dwayne Brown up at MI and stuff in Canada, and just really the best of the best. There was our mass lab, our electrical lab, our vacuum lab, things that just of course, equipment that even a lot of people that spend their lives doing calibration don't get a chance to be around. If you work in vacuum metrology, you probably use capacitance diaphragm gauges if you're really doing high-end metrology. But if you work in really high-end vacuum, you're using a spinning rotor gauge or a molecular drag gauge, where you magnetically levitate a ball bearing that's in a tube inside your vacuum chamber, and that ball bearing is a magnetic dipole. So you spin it up using a magnetic field, and then you let it hovering there, suspended by a magnetic field, and it's sitting there spinning, and then you have a detector on it, that detects when the North and South Pole kind of go around. And the only thing that'll make that ball slow down is molecules of gas inside that chamber. So it would spin forever if you really had a perfect vacuum in there. And so the way
Wow.
you determine how much vacuum you have is just that, it's how quickly that ball slows down. So it's just stuff like that, that and I'm not a vacuum guy, but yeah, and the list goes on, with the stuff. All of our labs were equipped with high-end stuff. And, I started there in 94, October 94. And in 97, we got a Josephson voltage system there that NASA had given some money to NIST and Sandia National Labs to kind of make the idea of a portable Josephson voltage system. So yeah, if for a lot of people listening probably know what that is, but it's a kind of a quantum cryogenic superconducting apparatus that generates voltage very accurately. It generates it in quantum step values of roughly 150 microvolts, but the voltage that you're generating only depends on the fundamental electron charge, the Planck constant, and the frequency of a microwave radiation that's usually at 70 plus gigahertz that you're sending down this probe that you put into a liquid helium dewar. So you're operating about 4 Kelvin. There's a superconducting chip down there that was made by NIST. And so again, this was all NASA money that kind of made this. NIST had been operating Josephson systems for a long time. But this money was made for a portable system. The idea is that the 12 NASA centers around the country would kind of ship it between them and stuff. But yeah, you're
That is so
never going to
cool.
be exposed to stuff like that. If I had just gotten a job working at like a commercial calibration lab, which would have been fantastic, and I would have, invested myself in that. But I really did just kind of stumble right into the mother lode of awesome metrology when I
Yeah.
went to work there. So
That's incredible. Yeah, because I mean, we have some students at this point that are going through level 2 stuff. So some of the industry is getting exposed to secondary and a little bit of primary calibration in education. And so some of
yeah.
the words you're saying they will recognize, but I'm sure their heads are spinning thinking about things like the highest high end, right? Where, I mean, you can attest for it. Are you in a rush when you're calibrating there?
Definitely not. I'm sure Henry's not speeding through calibrations as well, um, yeah. So
There's a lot of
No.
factors that you want to definitely slow down. Now, I had written down the Hubble. You worked on the Hubble project, is that correct?
no, I had zero to do with Hubble.
Oh,
So
Henry, what were you talking about? Did
Oh,
I mess it
yeah,
up?
no, Paul's done. Well, I wanted to ask Paul. Paul knows I'm a huge fan. I had to look some things up for Paul.
Oh,
We need
okay.
to get some things in here that he needs to talk about his time with. And one of them is the Patra ZB measurements that you did.
oh, yeah, those were the most sophisticated measurements ever undertaken. Yeah, no, so that Patrazibi, I don't know how you actually pronounce it, but yeah, it was kind of a running gag in a Mad magazine. It's a unit of measure, supposedly equal to one of the issues or volumes of Mad magazine back in those days. But there's a whole story behind it. There's a mathematician, I think his name was Newt. And there's whole notation about incredibly, if you ever go down the rabbit hole of large numbers, that is a fascinating kind of thing. I know this is a metrology podcast, but I got kind of really interested in that at one. Like a Google, which is 1 followed by 100 zeros, is like way more than the number of atoms in the known universe. But a Googleplex is 1 followed by a Google zeros. Like you couldn't write the number a Googleplex down in 1,000 lifetimes, much less count that. And a Googleplex is not even remotely in the realm of large numbers, So Newt was a mathematician, a guy, a professor that kind of came up with a Newt arrow notation for this for super large numbers. I mean, ridiculously large numbers. So,
So what
yeah.
did people use? So did someone just go through and create them for like theoretical science type stuff? What are
No,
they?
there's there's a large number, Graham's number, which is kind of usually talked about as being the largest number that's actually been, had an application in mathematics, but usually it's in statistical
Hmm.
problematic, statistics and things like that, where you're just talking about infinitesimally small probabilities and things. But and I'm not a mathematician by a long shot, but I do find a lot of that stuff interesting. So yeah, so the whole Protsbury kind of Mad Magazine unit of measure. Google used to actually would convert dimensional measurements into units of Protsbury, but I don't know if that's
Is that how?
still the
Yeah,
case.
yeah. But yeah, Paul sticks little tidbits in his presentations now, Easter eggs. He did it long before Marvel started with their movies. But if those that are listening here, I'm off to the side having to look up things where Paul is like the walking. A lot of people have referred to him as the walking encyclopedia set of
Yeah.
metrology.
Yeah, I was the Z volume that was about the X volume that was about 3 pages long.
You're right. Yeah, thousands of pages. So we could just talk. So we talk about and Ryan, some of the things that Paul did with his education and outreach over the years with Kennedy, and then with what you were Baxter, then and then Abbvie, and some of the other ones, is really passionate about outreach and some of the papers he's written. Of course, I've referenced numerous times because they're just absolutely fantastic, and we could talk for, if anybody ever sits down with Paul, you can, 5 hours, 6 hours later. The last time we were at NCSLI, I felt bad. I think we sat down, Paul, at 8 o'clock at night, and it was 12:30, and I was a bit tired, and I went upstairs. And I'm like, man, why'd I come upstairs? And I'm texting Dilip was with us. I'm texting Dilip, are you guys still down there? I'm regretting my decision to come upstairs. and Dilip's like, no, we're leaving. And I said, okay. I was like, I was going to come right back down because of some of the discussions we were talking about. We were having some risk discussions and some other stuff that we can talk about. But Paul did some presentations, and I think most recently on the Spirit of Kansas, and the other one he did on the Hubble, and the overall. These things happen. The Spirit of Kansas was a stealth bomber, $1.4 billion that crashed. And Paul was just LinkedIn messaging me a lot of this because I had known about this, and I presented in the risk course. And then Paul fills in all the blanks, right? Because we hear what you hear in the general industry, you look it up, is you say, hey, intertwining winds and stuff cause the reactive with the sensors cause us to lose a $1.4 billion plane. But then Paul takes it, and Paul does all the research, and I'm going to let Paul talk on this, and we can discuss the two things: the Spirit of Kansas, why that crashed, and we could also discuss the Hubble telescope, because they're both very much related to metrology.
Yeah, thanks. That's both great metrology stories. Great in the sense of lessons learned and stuff. And when I was at Kennedy, Scott Mims was the kind of the first one that turned me on to the the B2 crash. There was I think there was a NASA newsletter. It was basically like it was really short, but it was basically like a lesson. I can't remember. It was like a lessons learned newsletter. Again, 3 or 4 pages, real short. And so one of those newsletters had been dedicated to this B2 stealth bomber that had crashed in Guam, and they'd never had any real issues with that plane. It had a good track record of flying. So it crashed on like 27 seconds after takeoff. So pilots, everything's pretty normal. Pilots roll off, and they pull the stick back, and the nose just like juts up at this incredibly high angle of attack, and then and they're like in the stall condition almost, and they're not gaining any altitude. And then the plane starts it's not acting like the pilots think. It's all fly-by-wire, right? So the stick's not connected to anything. You tell the stick, and the stick tells the computer, and the computer tells the plane what to do. So then as soon as the left wing starts dragging the ground, both pilots had to eject, and they were both okay. One of them did suffer some spinal injuries and spend some time in the hospital and stuff. But so the story about that is so what caused that plane to crash? So it was at an air base in Guam where the plane was stationed. And so Guam is super humid, and it rains there a lot. And so a lot of times before the plane would take off, I used to hear our technicians out at the Space Center. A lot of them had Air Force PMEL backgrounds, and so we would calibrate air data test sets, and then those air data test sets would be used to calibrate the instrumentation on planes. And so fly-by-wire planes, they rely on the measurements and the sensors are their eyes and ears. If you don't have good data coming into those sensors, the plane cannot fly. So at any rate, the story of the B2 is that they were they were getting these, the plane would say, hey, they get these lights that say we need an air data calibration. And so some of the technicians, over the time that the plane was there, had realized that when they connected their air data, their standard essentially up to the plane, which would be the unit under test, for the calibration people.
Mhm.
So they would connect it up, and the plane would say, oh, it would say what its pressure sensors were reading, and it was way off from what their standards were reading. And this will be a good segue maybe into the Hubble, because both of these things can kind of touch on the concept of Bayesian statistics and how important that is in the realm of metrology and really in life, I would say. But if you're a technician and you hook a standard up and your unit under test is way out, and well, sometimes the unit under test is just way out, and
Yep.
that happens, right? We all have seen that.
Mhm.
But a good metrology calibration, guy or gal should maybe kind of question yourself: did I have it hooked up right? Is there something wrong? Do I have the wrong scale or the wrong range or whatever? And so I suppose that actually happened early on, and some of these guys say, hey, this thing's calling for this massive adjustment, and we just calibrated it like last week, and everything should have been fine. And now we're, a short time later, we're connecting up to it, and it's calling for this huge adjustment. So before these technicians just hit, yeah, adjust this plane sensors, to put this massive offset or to try to correct for supposedly this error, I guess they call the engineers, that it kind of been involved in the design of the plane, and they said, yeah, that is weird. And so they had them take some humidity, and they found out that, long story short, that it was humidity in the pitot tube sensors that was causing
Hmm.
the pressure values to be way off. And
Hmm.
so they were like, huh, that's what do we do about this? And so the pitot tubes have heaters on them, which are usually to, thaw out the pitot tube heaters, not only on the ground if there's, snowy weather and stuff, but also at altitude when it's very, very cold. They need to turn on the heaters to heat these up. So some of the flight crew had realized that if they flipped the pitot tube heaters on, it would bake that humidity out. And then they shut them off and wait a couple of minutes, and then everything was fine. And they actually didn't need to be adjusted. And so that's the real, my, I guess, impetus for telling the story, especially to the folks that I work with, because we have engineers that write procedures and techs that perform calibrations and stuff. Is okay. That's great that you learned this, that you should flip the pitot tube heaters on to bake this moisture out, to get rid of this huge offset in these sensors. Great that you learned that, but before you break your arm patting yourself on the back, document that. Write that down. Make sure that gets put in a procedure, so that when you leave or you get sick, and then John is calibrating, the comes out to hook up the air data test system in this plane and calibrate it, that he's going to know, don't hit that massive adjust button just because it says there's this error in here. You need to take these processes or these steps first to turn the pitot tube heaters on, so that you'll get accurate measurements. And so it really is more of a story about, documenting all correct steps. And I always say, and this is totally true, that measurement uncertainty is really not a number that's associated with a standard. It's a
Nope.
number that's associated with a measurement result that was obtained via a documented procedure and process and technique.
Yeah.
So yeah, and so the new technicians, they were following the procedure. It didn't say anything about pitot tube heaters. They
Mm.
didn't know. They did what you might say was due diligence, followed the procedure. It called for an adjustment. They hit the adjust button. It stuck this big offset or bias that really didn't need to be there in those sensors. And when the plane took off, its airspeed and altitude were all wrong. And so the computer is making decisions based on what the sensors are telling it. And they were just being fed wrong, inaccurate data that caused the crash. And
It is, yeah. It's just such a great example. I know Scott, who Mims you mentioned earlier, was
yeah,
was teaching risk-based classes, and then he came up with us, and he handed a lot of that material up, which we hope to bring more to the masses for those that are listening. But it comes down, Paul's touching on, it comes down to the right process, the right procedures, and the right requirements, which the requirements include the equipment. But I'm so happy you're bringing this up, because yeah, as it's really important industry wise, because as people are cycling new technicians, the old ones we had, we had this pandemic, some people retired. The average age was so high. We knew like all the seasoned metrologists were going to retire. And a lot of people have just done things that way for years. And like, Paul, what you're saying, like the pitot tubes is such a great example that everybody else probably in the organization knew about it. Maybe somebody retires. I don't know the whole story of how the technician got to it, but you would think along the lines of the process, right? If I look at history and this thing's been in 20 times and now all of a sudden it's way out, I should be going to engineering. I should be going somewhere, even though my procedure says to do this. But that is as simple as that may sound. It was a $1.4 billion mistake that could have easily been avoided and probably wasn't, because we're human and we have flaws. And it's really, there's a lack of training in a lot of industries, and this is one of the worst cost-wise examples of $1.4 billion of that. There's also hubris, which will segue into the Hubble then. But yeah, for everybody listening, I mean, what I wanted to expand upon Paul's, there's a great book. It's called The Checklist Manifesto. Highly recommend it. And that basically says put checklists at the back of your procedures. And why do you want to do this? Because if a seasoned tech or even like a new person there, they need that checklist to make sure they're following the steps. To ask somebody to read a 20-page procedure or 30-page, and I've seen some of these procedures, right? Paul, Ryan, you've seen them. They're just, they're unyieldy, right? No one ever wants to go back in and ever read it again. And then I've seen others that just have a few pictures that might get the job done, but probably aren't going to accomplish things for a very difficult calibration. So the Checklist Manifesto, which there's a lot about it and about how hospitals use them and infection went down and everything else, you get new members on the team, everybody checks things. And if you have that checklist there, it gives you that thought input. I've done this, I've done this, I've done this. Oh, wait, this section I don't know. Now I'm going to go back to section 5 of the procedure. I don't have to reread the whole procedure. Section 5, I don't know what this checklist is talking about. I'm going to refresh myself. Maybe I'm going to ask somebody for if the procedure is not clear. But for those out there, new hires are the best people to validate procedures, and that's where we want to stress, because you tell them if anything is unclear, let's address it. Because people that have done it, if you give a procedure to somebody that's done it for 30 years, they're just going to say, yep. And they're going to miss like probably 5 or 6 important things that they always do and don't think about, because it's like that muscle memory, right? It's just there and they're just going to repeat it. So a new tech's not going to have the faintest clue on it, and they'll question things. But yeah, let's as far as the stealth bomber goes, that leads to the other piece of the Hubble, which Paul's talked about. That for those that do not know, before Paul discusses it, the only what basically happened is the Hubble telescope was launched, and it estimated cost, there were things wrong with it, which Paul will explain specifically. There were things wrong with it, which costs, they say about $1 billion, but the estimates were about $2 billion to fly a mission back up there and correct the problem. And I won't spoil the surprise. I did say some hubris in there, but what we got out of it, what we got out of that $2 billion mistake was a very nice narrated IMAX movie by Leonardo DiCaprio. So we can be thankful we got that bit out of this mistake that Paul's going to go into detail on.
That's well, first, let me you'll have to send me a link to your checklist manifesto. That sounds really interesting, because I do think that documentation is important and stuff. But anyway, so to the Hubble there, I think most people know the kind of the story of the Hubble, but again, I know that there might be some younger folks on here that may have heard of it and not have lived through that and everything necessarily back in the day. But Hubble was one of the big missions for NASA, for the world, really, to put a telescope up there that just had absolutely unprecedented capabilities for resolution and stuff. And so and I should start out by saying as well, I'm not condemning the folks that worked on that. PerkinElmer, I think, was the contractor on at least that built the primary mirror of it, which is a huge mirror. It's just enormous. I forget exactly the size of it. I've seen the pictures, and I'm going to say that that mirror is it's 3 or 4 meters in diameter. It's an extremely large mirror, and the polishing of the mirror was something that even the cooling of it, the glass, I think it took like months or something to cool at a very known rate to reduce stress. And so it's a technological achievement that is mankind should be proud that we're able to even pull that off. But yeah, so the shape of it was a shape that was difficult to make as well, but it had some specific advantages regarding like chromatic aberrations and things like that I really don't know a whole lot about. But the design of it was such that the shape of the mirror, like any telescope, is super critical. And so as they kind of put this initial grind on it to kind of form the shape of the mirror, there's there's some checks that they go through and stuff. So during production of the mirror, they made a few measurements on it, and this like the first measurement that they made, and they made 3 different measurements as what the story is really kind of about. We'll just call them method 1, 2, and 3. And so the first measurement method that they used on it showed a very significant offset, about an order of magnitude roughly greater than the specification called for in a mirror. So something was clearly wrong here. And I say clearly, but this measurement technique had a rather large measurement uncertainty associated with it. The measurement uncertainty was actually larger than the specification of the mirror that they were trying to hold it to. However, the accuracy compared to the magnitude of the error was still easily good enough to show them that something was wrong. I wish I had a diagram, but if you picture this like with an upper and lower control, not a control limit, but an upper and lower specification limit or something, right?
Yep.
And let's say that this, your tolerance is plus or minus 1 unit, whatever that unit is. And so maybe your measurement uncertainty of this first technique is plus or minus, 2 units. You have, so the measurement technique is like twice as bad as the tolerance that you're trying to measure. But if that offset that you measure is so far down and you're looking at an error of like minus 10, well, even though that your measurement uncertainty is like plus or minus 2, that the magnitude of that error is such that should cause a serious amount of investigation as to why this error is there. And so they brought in there was a second measurement technique that was used on this that also had a rather large uncertainty, but the magnitude of the error agreed very well with the first measurement that they had made. So now they have 2 independent measurements that show this large negative error in the mirror. But they had this third technique, and it was the technique that had, I would say, the potential for the lowest measurement uncertainty. It was a laser interferometer that was used. They had the mirror in a jig, and it's been a long time since I looked at it, so I'm going to use some words I really don't know. But there was a metering rod that was, I believe it was an Inconel metering rod. It was a metal rod that was precision manufactured, polished ends on it. It's essentially a gauge block, like a really long gauge block, maybe 10, 12 inches in length, something like that. And so the idea is that when they had this fixture and they chalked the mirror up in this fixture, they were going to measure it using this apparatus where this metering rod was kind of an integral piece of the measurement accuracy. And on the end of this rod, they had, it was a cap that was, it almost looked like a top hat that the rod would go into, and that end cap would positively locate the metering rod in the system. And then the cap had a hole in the end of it that the metering rod, that you could see the very polished edge of the metering rod through. The idea was that they would shine a laser and bounce it off the end of that metering rod to positively measure, the shape of this mirror and all these critical dimensions. And so they actually used that as they put all their eggs in that basket, right? That this was their expensive interferometer system, and this was going to tell them. And so they did the final checkout and everything with that system, and final grinding and polishing in the mirror, trusting that system. And in the end, it turns out that cap that located the metering rod with that hole in it, the surface of it that was where the laser was kind of, you would say, incident, was coated with an anti-reflective coating so that it wouldn't, no light would diffract off it or anything. But the laser was supposed to go through the hole and bounce off the end of the metering rod, not off of the cap itself. And so that's actually what happened, is there was a misalignment in the laser. It bounced off the end of the cap that was used to locate it within the jig. And so, and that's what caused the mirror to be ground to, oh yeah, Henry's actually got some stuff pulled up here. Wow, that's
Those that are watching on YouTube, we can dissect this
Well, hold on. Let me get rid of me. There we go.
a little bit more if I have the right screen. But
it's actually been a little while since I've looked at this there, Henry. Yeah, nice job pulling that up there. I've actually got my laptop here. I meant to be a little better prep for this and to have a few things I could pull up to share, but
well,
yeah.
Here's what we're talking about: the RNC, RNVC, and the INC. Right, that's what you were talking about, Paul. So 2 measurements showed that this mirror as built was way out, and the RNC, which was much more accurate, right? Specification was bad, as far as because of what you described as that meter rod and the cap. They didn't get it right. But
yep. It's almost like we were talking about before with the B2, it's almost like if you view these not as 3 different measurement techniques, but 3 different technicians had come up and made these measurements. And you got one technician that's kind of new, he just started a month ago, but he follows a procedure, makes it and says, hey, I see this large error, right? But he's new. So you get the, so maybe the second calibration technician, maybe she's been there a year, and you say, well, can you measure this? And she measures it, and she gets the same result, this big error. But then, you take your 20-year-old veteran who you have this ultimate trust in, and he says, nope, everything looks good to me. And nobody ever asks, well, why did those other 2 people see those large errors, And so the same thing is true here. Yeah, those first 2 techniques, that INC, that inverse null corrector, and the refractive null corrector, the 2 techniques that showed the large error. If you look at the magnitude of that error, that is what really should have been investigated further, And again, I should say that I've kind of read the report and everything, and I know that there was huge pressures and scheduling and all of this stuff. We have the vantage point to sit here and look at it in hindsight and, and tear everything apart and, say, well, they should have done this and they should have done this. And that's
Right.
not the main point. The main point that I think I want to get at is that, you've got to ask why when you do see things. And if there's like Henry alluded to before, if you've got 20 years of data on something that shows that it's been in tolerance every single time, well, the first out of tolerance you see, you really need to do a lot of investigation to figure out, is this a real error, or is there something different? Is there a new technician, a new standard, something wrong with our measurement setup when you've got 20 years of data that says that something was good? And so,
yeah, and this can go both ways too, because we recently had this at our facility where we had about, I think it was 7 years of history. And if we looked at the 7 years of history, the first 5 years, there was a widespread in the data. The instrument, the reproducibility characteristic when it was calibrated was wide, resulting in a much larger error. Calibration number 6, man, everything, just the reproducibility was just spot on, and the error was super low. Right. And we think, oh, great, I just got lucky, right? Everything's good. It's still in specification, well within specification, but customers going to be super happy with this really awesome, really low error from reproducibility. Cal number 7 comes up and it's back to the first 5 years. And guess what happens when 7 comes up and the customer gets it? Well, why can't everyone be like 6? Right.
Yeah.
And then 6 probably needed more investigation, but we're less likely to investigate when things are showing really, really good.
Oh, yeah. And this happens a lot out there, especially in commercial cal, like a lot.
Yeah, absolutely. I think that looking at those bullet points in that last one, kind of, and that was right out of the report, that they were shopping for the answer that they wanted, right? Which is this, it's almost like this human thing, I mean,
Yep.
Arguably, philosophically, the right way to make a measurement is like when you do like an interlaboratory comparison and you're sent an artifact and you really don't know what the right answer is. And you have to kind of make a measurement. I don't want to say blindly, but you have to make a measurement without really knowing any history or what the right answer is. And so, that's one way to look at it. That's one philosophy. And I do believe that has some merit. But I do think that if you do make a measurement and you do have previous measurement data available to you, that, and this is kind of the Bayesian statistical philosophy, that to make the best estimate of something, you need to incorporate all available data.
Right.
So if you measure something and there's an error there, you could just say, well, I see this error. I did the procedure. I followed the procedure, and I think I did everything right. So therefore, I conclude this item is out of tolerance or doesn't meet its specifications. But if I came up to you and I told you, okay, well, you started here 3 months ago, and you say you followed the procedure correctly, and you made this measurement, and you see this out of tolerance thing, would it change your mind if I told you that we've been calibrating this thing for 40 years, and that over that time, 18 different technicians have calibrated this thing every 3 months? So we have 150 calibration events on this thing, and they've used different standards over that time, and it's been measured in different laboratories, and we've never seen this thing out of tolerance. Well, that should cause you to do a little more due diligence, maybe, to check that. I think Ryan brought up a point that you hear from a lot of quality people, which also has some merit, which is, well, if you're questioning or double checking your out of tolerances, why aren't you questioning or double checking it when you find it intolerance? Right?
Right.
That has some merit to it.
We
But
just passed. The majority of labs are just passes.
and I think that's the answer, though, is that why that we not only humanistically feel that it is the right thing to do to question out of tolerances and large errors more than to question intolerance results, is that by and large, end of period reliability shows you that intolerance is the norm. That is the expected outcome. And so there is some credence that says that, it's when you find these anomalies, these low probability events, that it should rightly cause you to say, I'm going to go back and look at previous data. I'm going to make some more measurements. I'm going to get a second set of eyes on this. So,
Yeah.
I think there's a lot of good philosophies there on all sides.
Great ones. And then here's the other one that for those that are online, Paul, that these came from your slide deck. So
And
Yeah,
I
if any of you
obviously
are
took them out
wondering,
of that report. Yeah.
if any of you are wondering what we're referencing, you'll have to go to about 40 minutes on the YouTube video where you'll see we have some slides up.
yeah, it helps. Like some people can, and Paul is just excellent at describing things. You sit down with them, and other people like myself and some others, sometimes we need visual aids, but this I happen to have to pull up. That's an aid. And I think for those that are not getting it completely, they just come on at 40 minutes in and look at the two slides that we're showing here on what potentially happened, or what did happen with a Hubble.
Yeah. Yeah, I think further on there's there's a diagram of the metering rod and the end cap, and even showing the flaked anti-reflective coating, on it, that really kind of gives a good idea of what happened there. But yeah, it's kind of funny when I kind of read through this report, I was at one of the annual NASA Metrology kind of workshops and stuff that we used to have each year. And I was kind of just surfing around, to be honest, while there were some, other, we'll say, administrative presentations going on that, didn't really have a lot to do with, metrology. And so I found that report, and I just thought, it just dawned on me, now, one, if you search the report, again, metrology is mentioned, 20 something times in that report. But it is a good example. I keep using this phrase, Bayesian statistics and stuff, and what it really means. And those three measurements on this, and Howard Kastrup is really the one. He was a great guy. I haven't talked to Howard in a long time, but he's just such a great guy, and do miss chatting with him. But he's the one that really kind of turned me on to this, and it will change the way, I guarantee, that you view metrology and calibration for the rest of your life. And what he said, and what I believe, and I think what is almost inarguably true, you just have to, you're going to think, well, okay, that is true, but it's just too difficult to implement in the calibration world, certainly. And that's this idea of this. So we take those three measurements from the Hubble. So you get three measurements that have three different answers. Now, granted, two of them were in pretty close agreement. One of them is pretty far off. right? So this is kind of what we do every day. We make measurements and we compare things. So let me give you guys a setup real quick. And I this has it's so we'll just keep thinking about the Hubble because it's really what it's the example that we're using here.
Fair enough.
So and I know Henry's a force guy, and Ryan, you probably have a background in all types of metrology. I don't know exactly what your
pressures
forte
is right.
Pressure,
temperature, actually. Temperature is probably one of my favorites. Yeah.
Temperature and pressure.
Let's just use temperature because that's a fascinating field.
Kind of universal for everybody.
Universal, right?
It's cold.
So it's actually the perfect example because this is, I don't have to say, well, imagine this. This actually is the way that most temperature metrology is done, is that you have some oil bath, some fluid bath. You can use chambers too, but air chambers. But let's just say you have this oil bath that is a temperature controlled oil bath. Now, it's not your calibrated standard that you're going to just stick a unit under test thermometer in and compare it to whatever the thermostat on your oil bath reads. That would be insane. So you use your oil bath as just the uncalibrated, inaccurate stimulus, the physical stimulus to apply to a unit under test thermometer and a standard thermometer. And you might even band these things together so that they're in super close proximity. You might use an isothermal block that they're both down in a big hunk of aluminum or copper so that you get good uniformity. But the idea is that to calibrate the unit under test thermometer, which is an indicating device, it's going to indicate temperature, that you're going to compare it to a standard that's also an indicating device. So you got two indicating devices and this uncalibrated source of physical stimulus that you're putting in here. So we get absolutely dedicated to the idea that we have one of these as a standard and one of them as a unit under test. So if I say that, well, one of them reads, let's just say 11 degrees, and one of them reads 9 degrees, and that's all you know right now. And you say, well, what do you think the real temperature is of that oil bath? Well, which is your standard? Which is the unit under test is what we might ask. Well, let's just say that these two thermometers have the same uncertainty specification or the same accuracy specification. And they both have been calibrated for 20 years, and they both have 97% end of period reliability. So their reliability is the same, their specification is the same, but one of them reads 9 degrees and one of them reads 11 degrees. And your life depends on it. So you have to say, what is your best estimate of what the true value of that oil bath is? You have no choice but to say 10 degrees. I mean, any other thing you would have to say, if you said 9, you would have to give some reason as to why you trusted that thermometer better. Or if you said 11, you would have to give a reason as to why you trusted that thermometer better. But
it'd be 50-50.
50-50. Right? So the
and 10 splits the difference. So worst case scenario.
That's right. So I like to think of this as you have two voters. You have one thermometer that's voting 9 degrees, and you have one thermometer that's voting 11 degrees, just like the Hubble. You got these different measurement things that are voting. I think that there's a big error, and I think that there's no error. Okay.
That one's a little different because we had 3 measurements and 2 were showing not so good, but it's good.
That's a great point, Henry. It's a great point. So it'll be a great point to extrapolate, this kind of introduction into my mind about how I came to the realization of what Howard Castro was talking about, because I'd heard him mention this, Bayesian kind of concept all these times. And I was like, he seems like it's really important. So what is he talking about? And so, so if you've got this situation, 2 thermometers, same specs, same reliability history, 2 different readings, your best estimate of what the measurand or the oil bath really is would be 10 degrees. But now if I told you that, well, one of these thermometers has an uncertainty spec of 15 parts per million, and one of them has a specification of an uncertainty of 20 parts per million. So one of them is 15 and one of them is 20. One of them is slightly less accurate than the other one. Well, now what's your best estimate of the oil bath? Does that little bit of better measurement uncertainty make you change your estimate from 10 degrees and just put all your eggs in that basket of this thermometer that has plus or minus 10 parts per million uncertainty versus the one that has plus or minus 15 parts per million uncertainty? It's like a good question, right? They're both
very good question.
Maybe it makes you think 9.9 if the better one's 9 degrees.
That is exactly right, Henry. So now, one's reading 9, one's reading 11. And so instead of 10, Maybe the one that's reading 9, that's got the better uncertainty spec of 10 ppm, you say, like Henry says, you start to sway your estimate a little bit more towards the one that's got the better uncertainty, right? So, end of period reliability is another thing. If one of these has a better specification, but it has a really poor reliability history and it hasn't met that specification very often, you start to kind of lean towards the other one, right?
Yep. Especially if the other one has 20 years of meeting and this one's been all over the place, you're just going to, the assumption is you're going to fall into the trap. The assumption is the one with the good history is the one I should go with. So therefore
right.
I'm going to go with that. And statistically, you're probably right, but the word is probably right.
Well, and exactly right. So what does probably mean? What we're really talking about here is we got two measurements, different measurements, two voters that have said different things. And so the idea is there is a statistical way to say, well, how accurate is this one? And how accurate is this one? And then what is the average of it? And it tells you how far to pull your estimate towards one of those or the other one. You can extend this to 3 items or 4 or 5. If this one's got plus or minus 20 ppm, plus or minus 15 ppm, and this one's got plus or minus 2%. Well, that 2% guy over there hardly gets any vote. We're really going to pay very, very little attention to him once we figure out what the aggregate or the best estimate of the measure end really is, right? These other ones that are plus or minus 15 ppm or plus or minus 10 ppm, we're gonna give more credence to them, right? So what we've just described here is any measurement process where you have 2 measurements, that there is a way to arrive at the best estimate of the measure end. But we never do this in metrology. We call one of them our standard and one of them our unit under test.
Right.
And we put all our eggs in the standard basket, and we believe that whatever the standard tells us is the, quote, best estimate of the measure end. We can never know what the true value is of this oil bath, but we put all our eggs in this basket.
And now, not only do we do that, Paul, but we adjust the unit under test.
A lot of times we do. And in fact, for Ryan, for PRTs and platinum resistance thermometers and things like this, we almost always make an adjustment because we almost always reassign ITS 90 temperature coefficients to PRTs, as certainly at the high levels of metrology.
Well, even lower ones are changing to 0. The zero value.
And that's it's a good point. I always say there's a element or measurement disciplines in metrology where it's just customary to always make an adjustment or assign a new value. Microwave power sensors are a great example. Send them into, Keysight, they're going to give you new cal factors for every frequency every single time. They're never going to go, oh, this is intolerance. Just keep using those cal factors you've been using for the last 10 years or something, So the idea of this, what I'm describing here is that if you have like 100 to 1 test uncertainty ratio, placing all of your eggs in the standard basket and trusting the value that your standard reads completely and totally ignoring the unit under test is probably valid. Because again, if you got 100 to 1 test uncertainty ratio, the uncertainty of that unit under test is contributing so little to your overall knowledge of what that temperature really is that you should in fact practically discount it. But
you're comparing an SPRT to a thermocouple, you're pretty safe.
Exactly. That's a great example, so these things that have, and hopefully in most metrology, those are the comfortable areas. But in areas where somebody sends you a 3458 digital multimeter that measures voltage to, 4 parts per million, and you might have a 5730 calibrator that can produce voltage to 2 parts per million, your uncertainty ratio might be 2 to 1, might be 3 to 1 or something, right? So we guard band, which is good. That's a whole nother subject, super fascinating that, we could talk about. But we guard band, but we still say, even in these situations where if this calibrator, if you set it to 10 volts and you put it into this 3458 digital multimeter, that is your unit under test, you're trying to estimate how much error it has. We just believe our calibrator. We believe that calibrator is outputting 10 volts. That's what our standard says that it's outputting, and we would think it would be heresy to actually take the unit under test that this is the unit that we're calibrating, and let that item have a vote in what we think is the actual true measurement of that value of that voltage. But in fact, that's really what we should be doing. All our calibrations, we should let the unit under test also vote based on its history and its specification or its measurement uncertainty. And it's just this concept that kind of blew my mind when I first realized that this is what Howard Castle's been talking about. Is that's kind of the right way to do metrology. If Hubble had done that, they would have said, even though these two other measurement techniques that don't have very good accuracy, because of the magnitude of that error, we need to update our estimate of what we think the error in that mirror really is, and not just put all our eggs in this one basket over here. And if they'd allow those two measurements to vote on what the actual shape of that mirror was, they would have had a, that's really what should have occurred, in my opinion. But
Yeah, it should have. And your points are fantastic. And what should really happen, right, is if we have that UUT with a long history, immediately when that's showing out and we have this long history, maybe we bring out our check standard.
yes,
Right. That's
absolutely.
probably, let's look at our SPC charts where anything on our end. Are there any clues or anything to make us feel more confident? I always look at the measurements we make, and sometimes our team that dislikes me is like guilty until proven innocent. Right. We got to prove that this measurement is valid and yes, we fall into the trap like many do. If something comes in and it's good and it's been good previously, it goes right. There's really no need because the risk is low to make a second measurement.
Yep.
But yeah, the main thing that I can't stress enough with our techs and stuff, and it's part of our process. We have it bolted up on our lab. I think it's step number 6. I should know these. It's 3 or 6, which is always check previous data.
Yeah.
Right. And then some people say, well, you're influencing your technicians.
Right.
So if you do that. No. I mean, if we're influencing them on anything, it's what to look for. That's the influence, right? Oh, this thing's been, there is some influence on if it's been good or bad, and now it's bad. It's like, well, it has a history of that. But that, to me, I get less stressed out if I know it has a history of that. If it's 10 years it's been good and now it's bad, maybe I'm not pulling my check standard out right away. I'm looking at it to see if there's a big gash or a dent or
Yep.
any visual signs of
Sure.
damage that more clues. But as soon as that happens, the investigation hat needs to come on, and it needs to be like, okay, am I going to, what happened? Am I going to call the customer too and say, hey, has anything changed? And you may find that they did something stupid with it. Oh yeah. I mean, I remember going down the rabbit hole on this one that I called the customer when something happened, and he said, oh yeah, Joe dropped that. And
I
I
was
was
going to
like,
say
oh yeah.
dropped. Dropped is
Yeah, they
always
dropped it.
someone dropped it.
Okay, yeah. And I said, does that happen frequently? And then you go down the long rabbit trail. Yeah, this guy, I can't get him fired. He shipped all the gauge blocks. He threw them all in a single case, not even in anything. And then you go down that rabbit trail. It's sometimes comical on some things, but yeah, a lot of times with all of it, you do need to investigate, and we need to do a better job investigating when things were previously have this horrible history and now they're showing that they're fantastic, right? Because
Yeah.
that's another outlier too.
Don't you
But
feel
yeah,
like, oh, sorry. I was
no,
going to
go
say,
ahead.
don't you feel like that can happen sometimes too if you say you have two 3458s, if you're a lucky lab, you have multiple,
right.
sending them to the same place, can't that cause similar problems? Maybe you should split something like that up, some of your higher level stuff. I know, like setting up our standards for temperature, since we're already talking about, do you know Martin DeGroot, Paul, by chance? He's
Um,
on the ITS 90 committee.
Yeah, I've read a lot of papers by Martin, and I think he even published a paper in another discipline. But yeah, I don't know Martin, but super respect the guy for what he's done there.
So he advises us on our temperature program, and I asked him, how many of these we use SPRT, so secondary standard was right now. How many of these should I get? And he said, well, the way we look at it, if you don't have 3, you don't have a measurement,
Right.
because at some point in time you will run into arguments between
Yeah.
things.
Yeah,
Yep.
absolutely. And those groups of standards, it's why in the voltage world, you have like Fluke 732B Zener references, then they sell a rack where you can put 4 of them in there. So it's super common to have 4 as your reference group. And at Kennedy, we had 5 Thomas 1 ohms, so 5 of them are our group, and we intercompare them all the time. And then you can kind of use the group mean as your real standard and see which one of your 3 PRTs is kind of going off and and drifting away, So yeah, it's all, like more voters, right?
Right. Yeah. And thermodynamics. I mean, there's a lot of places that don't understand, like going up above 400 degrees, you really need to be careful coming back.
Sure.
and what happens after that. But again, to your point, if you don't have those things written down, or you're not training in general, new people and documenting things, you're going to run into those problems.
Yeah, absolutely. Henry mentioned before, probably I would say out of all, my life, the thing that I like the best, the tool that I think is the most valuable in all of metrology is is a control chart, where you chart your history of things, because it really does give you a statistical way to evaluate things, but a very visual way. And we shouldn't discount our intuition when we see stuff. And even in control charts, there's all these they call them run rules sometimes, like Minitab even has, you can select which rules you want to put onto a control chart. What you're trying to do is detect a quote out of control measurement, right? So, what does that mean? And so there's all these rules. Shewart had, developed a few of them, but I think it was General Electric. There's a quality control handbook by GE that was published in like 54. They kind of set aside the 4 basic rules that a lot of places even use today. Like if you get, and I don't know what exactly the rules are. Again, you can vary these rules to suit your own use, but like if you have 6 readings in a row they're all monotonically trending up or trending down, that might be an anomaly. Something might be starting to trend. It's not just randomly distributed by common cause variation, or if you get, they break it up into zones, right? Now, what they did is they had like upper and lower control limits. And so they break it up into like zone A is like plus or minus 33% of your control limit. Zone B is plus or minus 66 and so forth, So if you see like 3 points consecutive in zone C, like close to a control limit, maybe something you might need to investigate that. Might be time to make an adjustment, right? Might be time to do something. And so, I think Henry and I have to, we've talked about, Churchill Eisenhart, which was NIST, and just a monster of an intellect. And in 62, he published, what was, in my view, from what I've read, of course, that was 7 years before I was born. But, it was kind of almost like the unofficial gum. It was like this paper that had been published. It was called On the Precision and Accuracy of Calibration and Measuring Instruments, something like that. We could probably look it up here, but he was really the one that I'm aware of from what I've read that up until that time, even metrology at NIST and metrology and calibration in the industrial world hadn't really globbed onto some of these quality tools that like Deming and Shewart at the turn of the century in the 20s and 30s, had been using in manufacturing. And so Shewart, I think, worked for Bell, because it's some of his papers I've gotten from the Bell System Technical Journal, which is just a fantastic archive. I mean, the Bell System Technical Journal is, I could just go on for hours talking about it, because that was like the think tank in the United States where they just let smart guys and scientists do pure research to play, basically to find out things that might be beneficial to to Bell, because they were so big at the time. But anyway, so these control charts to show you when something is acting odd, out of control, or might, is one of my favorite subjects. Kind of sleuthing out what is systematic, attributable cause in measurements versus random common cause variation. And I think it's one of the biggest fallacies of humans is we all the time, we say, well, I put 5 pounds extra air pressure in my tires and I got 1.5 miles per gallon better gas mileage. Did you really? Because why don't you just do this? Why don't for like 2 months in a row, every time you fill up, you figure out what your gas mileage is. And after you've got this long history, you can see you haven't done anything different, but you're going to get a different value every time you compute your gas mileage, right?
And is it cold? What type of roads are you driving on? I mean, experiments like Eisenhart and these guys knew it. Like, we got to set these experiments up. There's a Netflix documentary out now, You Are What You Eat. And it's like, does a plant versus a meat-based diet, right? And in general, the experiment is identical twins that they set up because they have the exact same genetic makeup. Because if you don't set that up, what conclusion are you going to draw? And they're both on the same workout routine and everything else, and all they changed was plant-based what a plant-based herbivore versus omnivore diet, and that's all they basically went after. But really good stuff. So as we're like talking about all of this stuff, I wanted to just tell the listeners we going in, and Ryan and we all talked that this is probably going to be a 2-part episode. And in the second part, Paul mentioned a lot on control charts, which we'll still talk about today. But the second part, like discussing more on TUR, end of period reliability, what goes into this for the listeners out there that are curious. We threw out words like TUR, test uncertainty ratio, and stuff. And if people want to read Eisenhardt's paper that Paul recommended, it's the realistic evaluation of the precision and accuracy of instrument calibration systems. And if you just type in like Eisenhardt precision and accuracy NIST, the paper comes right up. I click the link; it's right there.
I can add the link into the YouTube
Oh,
description,
yeah.
Henry.
Yeah.
So I'll do that in the YouTube. If you're on podcasts, it's too hard to put that on all the platforms. But you can find a link over on YouTube. I was going to say, I love the talk of control charts and how we were doing temperature, because people in the school will probably be yelling at the screen. Temperature is a perfect example because you have to run your triple point of water and you do control charts on your SPRTs. But if it starts to get out of control, you anneal it, right? And it's usually from some sort of misuse along the way, unless you have one that just is getting a little unstable, I guess, over time. Maybe you have some sort of leaching, and there are things that change as we do cal over the years, especially a lot of those that are dealing with harsher environments, thermal dynamics, those things are going to change things. Literally, like the composition of the metals will change. And if you're not careful, then you will see your control charts start to go a little awry, and then you need to make some changes. So I love that. It's a perfect synergy, control charts, and we were already talking about temperature.
And it's a CYA, right? You're writing a control chart, so now you can do your CYB, cover your butt scenario, and you can have more read back to the measurements. If I'm running control charts, I have more confidence in that measurement. When that UUT shows that it's bad, I'm like, well, we're running control charts every day. We just ran the control chart. Let's do another test right now and just verify it right away. It's another data point on our control chart. And that's what Paul was mentioning. There's so much good stuff here that we can just talk about. But Paul did appreciate, and run rules. A lot of people, where I got at, a lot of people want like, hey, adjust this ASAP. They don't understand what their equipment's doing. They just adjust it to as close to nominal as possible every single time. Well, if it's going high and I adjust it, and I adjust it back to nominal, maybe the next time it's off the opposite way, low. And if I would have just left it alone, it would have been perfect the next time. So, I mean, this is a interesting topic by itself. Do I need 3 calibrations? Do I need 6? I think the SPC, the statistical process control, is started saying I need at least 6. Some people say 3, but I think their recommendation, I believe, is 5 to 6 measurements before you really get start to get a good grasp of it. Paul, can you have any of your thoughts on that?
Yeah, I thought, a ton about that because, we metrologists, it's like the old running joke, what do we want? Well, we want the customer to give us your thing that you want us to measure or calibrate for you, right? And then we want to measure it about 100 times a day for the next 20 years. Now, you can't have it or use it during this time, but that's what we want. We want to do this super where everything is controlled to figure out how is it really behaving and is it drifting and all this stuff, But yeah, a lot of times we don't have, that luxury. And, there's a whole nother conversation about, can you, group makes and models together to aggregate statistics. So, the advantage is you have more data quicker to make decisions on. The disadvantage is that you lose the uniqueness of how each individual instrument might be behaving. So there's certainly a trade-off there. But you're right, it's just such a all of these topics could be like a podcast on their own, because they're so interesting and important. But I would say that, one thing that when I was at Bachelor that we kind of, a whole nother story about why we went into this, but the adjustment of instruments, we'll just say, became a very big topic, right? For regulatory reasons,
Sure.
but so some people feel you have to. What if you had somebody that was in charge that said you have to make adjustments? And in fact, you're not even calibrating something if you don't adjust it. Well, we know how we all feel about that, but what if somebody said that,
So well, the VIM says calibration is not adjustment. It's very clear.
It does. So yeah, I think, we talked, I've got 100-page document with every single thing that I could possibly find in the published literature on the subject of adjustment, because it's, again, but what it did in a positive light is it caused me to really mentally, interpersonally kind of wrestle with this problem of, the dimming funnel, right? This statistical kind of mind, experiment where, you drop marbles through a funnel over a target and they drop, and then, that they'll have some natural spread. Well, if you drop one and the marble rolls, and of course it's probably not going to end up right in the center, but if you try to move the funnel to improve your accuracy, you end up just widening the spread.
Yeah, like 3 or 4 times or more, depending what you're chasing.
So the idea is even with a control chart, 2 things super important about a control chart is, you have to know, and to your point about how many measurements, if you're doing a real control chart, you have to know, what that natural common cause variation is, right? Under the given conditions. Now, if you
like your possible variation in a triple point of water, for instance, is that what you mean?
Well, and so that was the second point about a control chart, which I've said this, so many times, which was another revelation. I mean, what a control chart is, what we think or would like a control chart to be, is a chart that shows us how the unit under test is performing. But that is not what the control chart shows us. The control chart shows us the insidious convolution of the aggregated togetherness of how the unit under test is behaving and that our standard is behaving. Now, if our standard is 100 times more accurate or better, or our process, is super accurate, compared to the, how this crazy cheap unit under test is behaving, then yes, that control chart is almost overwhelmingly, almost totally telling us the behavior of the unit under test like we would want it to. But it's a great point. Once you start getting into super accurate standard platinum resistance thermometers that are treated very well by, very accomplished metrologists and stuff like that, you're kind of lucky in the temperature world in that, you've got these water triple point cells that are almost, perfect. They are an intrinsic standard, but because they exist in the real world, there are these, microkelvin uncertainties, and kind of behaviors, your ice mantle, whether your ice mantle is loose or whether, there's all these things that
isotopic stuff in your water.
Right. The isotopic concentration, what it's all water, but how much is deuterium? How much, all of this kind of stuff. It's pure. You filtered it is 100% H2O. But you're right. There's an isotopic.
That's the part I love about metrology is how deep you can always go. You can keep peeling,
You can peel forever and you'll never get there.
So you look at that control chart on your SPRT and you think that's how my SPRT is behaving. And it probably is because, these effects in a water triple pointer, again, so much, we'd like to think, so much smaller than what's going on with our PRT. But, in the electrical world, voltage, okay, you're going to take a 3458 and I'm going to track it. I'm going to do the thing because we have computers and we have automation. I can make 1,000 measurements a day for as many years as I wanted to, So I'm gonna put my voltage source into it. I'm gonna track this 3458, but I'm not tracking the 3458. I'm tracking the 3458 and my standard. Now, hopefully, I have a Josephson voltage system. I'm super lucky, and I really am looking at just the behavior of the 3458. But it's almost, without a Josephson system, it's almost impossible to really track the true drift of a 3458's own internal voltage reference because your own voltage references, your own Zener voltage references are drifting. Now, hopefully you've got 20 years of history on your Zener references. You know exactly how they are drifting and you're compensating for that drift. So again, your control chart is really showing you how that 3458 is behaving. But there's a bunch of ifs and gotchas and only if and under these circumstances and blah, blah, the list goes on and on.
Yes, a lot. Though the other thing that we're not mentioning on control charts here is if I do have an out of tolerance or ever have an out of tolerance condition, I can go back to that control chart And basically, instead of looking at, if hopefully no one's letting their standards go 2 years, unless that interval at your end of period reliability and all the other stuff dictates that 2 years is appropriate. That's a whole nother discussion. But if I have, we'll just say we've gone 2 years and I get an out of tolerance, well, when did it go out? Right. I mean, there are mathematically bootstrapping, and there's a lot of other things there that people know about. But the easiest thing, just plain and right and easy, is I have a control chart. It's shown this thing has been tracking, and it's started tracking higher in April, and my 2 years was June. Really, you could slice it up probably and say, look, April is where anything to April is where I'm going to look at. Even better yet, maybe it's tracking the whole way through and something happened in shipping, or the lab performing the calibration didn't do it right, because your lab performing the cal is not 100% right all the time. And they tell you something's out of tolerance and you say, no, retest it. Right. My charts, before it left, I did a measurement and it was good. And I measured it against 2 other, if you're fortunate enough, and I measured against these other instruments and it was good. We've had this numerous times with temperature. Maybe it's a new technician, someone doesn't know how to use something. They erase the current previous coefficients that have been in there in our boxes. And we're like, yeah, we'd notice, you're saying it was 5 degrees out. Yeah, our people would notice a 5-degree differential in the laboratory. You know, it would be much colder than the 23 that we keep it if it was 5 degrees C. So there's no way we believe this. And on top of it, we've checked it, and they were showing within like 0.2 to 0.2 degrees C of one another. And that's might be why we sent it out, because it was climbing a little bit. But yeah, you can really limit your liability with good control charts. And then once you have control charts, if anything ever happens, your wish is, oh, I wish we would have had taken these measurements weekly instead of monthly, because now you're going back 3 to 4 weeks instead of maybe 5 days maximum. So just all good stuff. Control charts are awesome.
And this stuff can come in huge, and I know I've mentioned it before, both in the school and in the podcast, but you got a lot of places going out there doing daily measurements outside of a lab and things like that, right? Keeping with the theme, temperature, if you have something that is a good standard, maybe still under like a calendar calculation or something that uses an ice point, but labs are going out there making these measurements out in town. A lot of things happen, things get banged around. Technicians are unscrupulous sometimes using their probe as a drumstick. No, I'm just joking, but things are happening, but labs are not doing any checks at all from cal to cal. And that's why I've been a huge advocate of, you got to run those triple points at least weekly, or if you're doing things that relate to an ice point, you got to do those, I would say, before and after work every day to really CYA, right, Henry? Where you're saying,
oh yeah,
I know nothing happened today that has, because there's labs out there adjusting or measuring the sterilization machines or whatever, where they need to be within a half a degree, and those temperatures need to go over. So there's a lot to consider there. You can't adjust where it goes lower than that. It has to be above that value. There's a lot of complications there. And if you aren't controlling your process and just letting people out there go and do their thing and come back, and it's getting stored in the van and it gets banged around all the time, and you're doing nothing to control that or to check that, I think you're going to have some major issues.
Yep. And it's all risk-based, right? You start every day, you think nothing's changing. Go to weekly, nothing's changing. Go to monthly, nothing's changing. Maybe it's every other month. What is your risk? Because sometimes something without a doubt is going to change. We had a customer, I think I told this story before, they always sent 2 instruments in, and we visually could see this. Every year, this one was creeping up and the other one was just asymptotic, right? It was just like a straight line. It wasn't moving. When they finally had a out of tolerance, and we could see this in our lab side, it was just when I analyzed the data, just creeping. When they finally had an out of tolerance, they said, we need to come in there and witness you do the cal immediately. And then we said, okay, we're going to do this. And I said, why? And he said, because it's $1 million problem right now. If this thing's actually out, we're going to have to go adjust $1 million worth of bolts. And we said, fine. I said, you had history. I wanted to say, didn't you look at your data, and why didn't you use the other one? Because it was clear that the other one was, and sure enough, came back, read the same thing. It was out. And the guy's face was white. He's like, I can't believe I have to do this. And I was like, yeah, he had to do it.
Yeah, you get to see the, the real business end of it when, we
Yeah.
all like metrology, but you really are hung out there where you've got people that, where it's super important and there are millions of dollars or B2 bomb or, all this kind of stuff that's
Yes.
on the
Yep.
line
Yep.
riding on these measurements, and, but I think we all think, well, if there's $1 million riding on it, why don't you have like 5 of these things? Right?
Well, that's a good segue into ending this one and going into the next one on choosing the right and appropriate standards, as well as end of period reliability, TUR, and all that stuff. But before we do, I have to ask something funny of both of you, and I'm bringing this up because you're talking about temperature. So, what's your favorite song related to temperature?
Oh, wow.
I'll throw mine out there. It might be Hot Blooded by Foreigner. I think that one's.
God, that's a great one.
But you can't have that now. I mean, you can't piggyback.
404 was my first concert. I was 13 years old and I saw Foreigner 4 in Tucson, Arizona. Brian Adams opened up for him. Yep. So yeah, that's a great. I'm gonna.
Because
I don't know if I can
we
follow
didn't
that.
start the fire count.
You can, yeah, why not? That's fine. That's temperature, right? I guess we can stretch it to that. Cool and the Gang's Too Hot. I was pegging you for that, Ryan, but
Yeah, you're right. If I had more time, you put me on the spot,
yeah.
It's, so I don't know
Nelly,
if you
Hot in
voted,
here.
Billy
Oh,
Idol
yeah.
did Hot in the City.
There you go.
I
Yeah,
don't know.
Paul loves the guitars of Billy Idol and Hot in the City.
Do you remember
Yeah.
that reggae guy, Sean Paul? He did one Temperature or something like that.
Oh, yeah.
Hot in Here, Nelly, right?
Yeah. I
had
was thinking of that song. I didn't know
No
who did it,
reggae
but,
fans in
we
here. I
had
take it.
Beverly Hills Cop, Heat Is On, always makes me think of that one. There's
That's a good
Cold
one.
Blooded. No, it's Hot Blooded. That's the Foreigner. There's Cold Gin. What Cold Gin? Yeah, Cold Gin. That's Kiss, right? Yeah, Kiss is Cold Gin. What some other cold songs? There's some good ones out. There's some good temperature related ones out there. And then Ryan's favorite band, 98 Degrees. I didn't want to tell
Oh
all
yeah,
the
Nick
listeners
Lachey
on you,
all the
but-
way, right?
I was going to totally date myself. There's a Bon Jovi album called 7,800 Degrees Fahrenheit, but that's going way back.
That's good. That's a good one. That had the temperature. So
Speaking of which, I mean, you can't ignore that he's got stacks of Marshall behind him. I mean, are you a guitar player? You got a whole studio behind you.
I'm a professional poser. That's my second gig here. No, yeah, I mean, people ask me if I play guitar. I make noise, but I've kind of taken up drums here lately, so I haven't actually
Love
picked
it.
my guitar up in a while.
oh,
and-
that's what you're doing with
yeah.
those PRTs, the SPRTs that
Yeah,
Yeah, I
Ryan
almost
drumming
mentioned.
with them.
Here, let's see.
Hey, I'm all about rhythm section.
Rhythm's gonna get you, and we can go on with songs.
I'm a drummer and a bass player, so I definitely respect the rhythm section
Oh,
players.
great. Yeah.
Are you gonna let Paul drum us out here on
Yeah, yeah.
1? Drum us out, Paul.
No, sir. I was just going to say, since you're a drummer, so you have these, you need to take your prop into your next temperature class and say, this is not for measuring temperature.
Exactly.
TRT is not for.
Or hold a PRT up and a drumstick. Which one is for
Right.
drumming and which is measuring temperature? Can we differentiate the two?
Yeah, absolutely. Yeah, it's hard to tell new people. Like you can say these are really sensitive items, and you shouldn't bang these things around. And they pick it up and they go, oh, okay, and then they put it down like that. And
Right.
it's like no, like when you say they're sensitive and you shouldn't bang them around, they think, okay, I shouldn't play stickball out in the street with them, but they don't really understand that. Yeah, don't lay it down on a hard surface abruptly. Treat these things super gently.
Well, I know there's a lot of labs out there that if you're under 10 years or so, you're not touching the house PRT or SPRT.
Yeah.
It's one of those things they kind of keep out of the reach of the newbies.
Yeah, absolutely. I was like strucken with the fear of breaking a PRT because when I first went to work at Kennedy, and even though I worked in the electrical lab, we used PRTs to measure the 25 degrees C temperature of our oil baths that we keep our standard resistors in. So these are resistors that, they're sensitive to temperature. Well, they try to make them where they're not sensitive to temperature, but everything's sensitive to temperature. So you keep them in this oil bath. And that's the only temperature that they were ever exposed at, was 25 degrees C. And we used the quartz PRTs, the old LNN 8163, I think Rosemont.
The
8163s.
Yeah, the Rosemont is very famous.
Yeah. When 162s and all the I'm getting things out of the cobwebs in my memory there. And so yeah, the quartz ones. And so I just remember the guy telling me, these things are like several $1,000s a piece. And if you consider the calibration cost of them, they're $5,000-6,000. So don't break them. And I was like, so that struck the fear in me. And I've even heard it debated. You might have some input on this. It's kind of funny. High-end metrology temperature guys debate whether quartz sheathed PRTs are perhaps more accurate than their stainless steel and Inconel counterparts. And so, the people that make PRT say, well, they're the same element in there. And aside from maybe a little bit of thermal lag or, difference, it's the same element. But I heard a rationale that I actually think is probably true. If you did the statistics and looked at control charts, I think you would find quartz PRTs are more accurate with a lower uncertainty than their metal brethren, simply because when people pick up a quartz PRT, they innately treat it more gently because it's glass and it looks more fragile.
Yeah.
That that
Deceiving, right?
Yeah, that you're seeing that difference in the numbers. So
Well, and those metal SPRTs, when they're annealed, they look like someone burned them. And you're like, no, that's just the process to protect it. There's a lot to explain there. Yeah.
yeah, that's a good thing, right? Yeah.
That's a whole nother segment.
So did you want to go into that other topic, Henry? Hey, this is the end of part 1. We decided to do 2 parts of this episode. So if you're listening to this the week of release, just wait until Thursday and it will be released then. Otherwise, go on to the next episode. Thanks for listening.